All right, so now we know what the GCD is, and if you did your homework already, using the Euclidean algorithm, we can calculate the GCD of any two numbers. And now this theorem that we're about to do gives us another way to characterize the GCD of two numbers, and this is a really interesting one. So the setup to the theorem is we have two natural numbers, a and b. So that means they're both positive integers, and we're going to define a new set called P that's all these linear combinations of a and b. So this is all the numbers of the form x times a plus b times y, where x and y are integers. And we want only the positive ones, so we're also saying that xa plus yb has to be greater than 0. All right, so we define this new set P, and then we choose the smallest element in it, and we call it D. The theorem claims that that D, that smallest element, that smallest linear combination that's positive, is the GCD of A and B. All right, so the first question when you're looking at this is why is there a smallest element? So why is there a smallest element in P? And that's a pretty good question to ask. It hinges on something called the well-ordering principle. So the well-ordering principle says that every non-empty subset of the natural numbers has a least element. And notice that this doesn't work for Z, for example, or Q, or R. If we have a non-empty subset of Z, of the integers, we can go more and more negative with that subset, right? So like the integers themselves, there is no smallest element in the integers, and there's no guarantee that a subset of the integers has a smallest element either. But the natural numbers do have a smallest element, and any subset of the natural numbers will have a smallest element. So that's the well-ordering principle. Okay. So then the next question is, so P definitely is a subset of n because of that condition on xa plus yb being greater than 0 up there, okay? So definitely P is a subset of n, and so now we're wondering, is it non-empty? And the answer is yes, because a is a natural number. We were told that at the beginning. And A is definitely a linear combination. It's an xa plus y times b, where that x is 1 and the y, nope, I wrote that wrong. The y is 0 times b, right? So A is in P, and so P is not empty. So we need to check that it's not empty, just because if it was empty, we wouldn't have this least element D, right? But this is just a quick check that P is not empty, so it's going to have a smallest element because it's a subset of the natural numbers. All right, so this is one we are going to prove. The proof for it is a little bit messy. I'm going to get myself a new page right away because we're going to need it. But it's kind of an interesting one, so I want to work through this proof, and it will be similar in format to a proof that you're doing where you have to prove something is the greatest common divisor. All right, so if we want to prove this, we need to show that D is the GCD of A and B. So we need to show 1, that D divides A and D divides B, and 2, that D is the largest common divisor. Okay, and remember that largest guy. We had a way to write that down precisely. That was, if you have another common divisor, why does D have to be greater than it? Okay, so let's work on this. We're going to work on number 2 first, but if I want to make this a nice formal proof, first let's write out our assumptions. So we're going to assume A and B are natural numbers, and we're going to let P be that set of all xa plus yb, where x and y are integers and xa plus yb is greater than 0. Okay, and then we're going to let d be the smallest element in P. And what that means is, this means that D equals XA plus YB for some X and Y that are integers. So that's definitely going to come in handy. So D is in that set P. That means we can write it as XA plus YB. All right, so first we'll show X divides A. All right, so let's talk about A. We're looking at, we have this element A and we have this element D. So we're going to use the division algorithm. So by this division algorithm, we can write A as D times some quotient. How many times does D go into A? Plus a remainder, where R is between 0 and D. Okay? So now let's do a little bit of substitution. We knew that D was XA plus YB, and here's D showing up in this equation, so let's put those together. So thus, we have that A is replacing D with XA plus YB times Q plus R. Whoops. And so now I'm going to solve that for R. So R is now A minus XAQ minus YBQ. So I did a little bit of distributing and subtracting to the other side. Okay, and now I want to rewrite that one more way. So I'm going to pull that A out. So what I have is 1 minus XQ times A plus negative YQ times B. All right, so now I've written R as a linear combination of A and B. Okay, so because 1 minus xq is an integer and minus yq is an integer, all of those things are integers, this says if R is positive, then R and P. So remember, P was all the linear combinations, all the things that I could write in the form integer times A plus integer times B. And that's exactly how I just wrote R. Integer times A plus integer times B. So as long as R is positive, R is in P. But R is less than D, and D is the smallest thing in P. So that means R can't be in P. And that means that R has to be 0. Okay, so if R was positive, then it was in P, but it's not allowed to be in P because D was the smallest thing in P. So this is a little bit of a complicated argument. Listen to me say it a few times and talk through yourself to make sure it makes sense. All right, so what we're concluding is that R has to be 0. And I'm going to need a new page. All right, so where are we? So R is 0. Remember what R was. So up at the top, we had that A is D times Q plus R. So now A is D times Q plus 0, which says that A is a multiple of D. So D divides A. All right, which is what we wanted. Same argument works to show D divides B. So if we look back where we started, this first, we're going to show x divides a. What we did was we set up this little write a d times q plus r. If we instead do the same thing with b and trace that all the way through the exact same argument, we will show that d divides b, and that's something that you should try to write up on your own. Okay, great. So now we know, that d is a common divisor of a and b. All right, so now we must show that d is the largest one. And so that means if c divides a and c divides b, then c is less than or equal to d. All right, so how are we going to do that? So let's assume c divides a and c divides b. Then we had a previous lemma. It was lemma u in the textbook. If c divides a and c divides b, then c divides anything times a plus anything times b for any x and y that are integers. And remember that d was our element in P, so d equals xa plus yb for some x and y that are integers. So this means c divides d. Okay, so then d is a multiple of c, and since d is positive, we must have that c is less than or equal to d. If d was 0, remember, we could say that c divides 0 fine. If d was negative, we'd get into some weirdness, but since d is positive and d is a multiple of c, then c has to be smaller than or equal to d. And so what we have proven all together is that d is the GCD of a and b. All right, so this is a little bit weird, but what we've said is that the GCD of a and b is the smallest positive linear combination of a and b. And we're going to use that as an example, to do an example in the next video of how you kind of find that x and y. But for right now, I want to show you one other quick thing that we did to prove this corollary. So we proved that for any common divisor of a and b, it divides the GCD. And this is because we know d can be written as this linear combination by that theorem. So c divides d if it divides a and b. And so we get this little corollary that is something that you may have known, that any common divisor actually divides the GCD of the two numbers.